Time for another instalment on the power supply project I've been working on. So last time we looked at I found some problems with the dynamic response. That was particularly true with switching a load on and off on the output, switching that fast, and then looking at the output of the power supply. And there was an overshoot of about nearly 400 millivolts, which clearly wasn't acceptable. So I've spent some time now and done something about that and got some pretty good results, I think. So I'm quite excited to show you that. I'll take you through it now and take you through the process that I've been through, and then I'll come back and on camera and talk to you about the final schematic and what's next. Okay, so one of the aims here. This is, if you're just on this point, this is our output. This is just after this input amp here. What I want to try and do is I want to speed this up. Basically, want to narrow this time down because that should, if this circuit does have latency, if it does have poor bandwidth, which I suspect it does, then this will probably be wider. And also here, this output should more closely reflect this input, and I think that softening there is done because of the lack of bandwidth here. So in this circuit, I think what I'm going to do is I'm going to attempt to bypass between 1 and 3 here. Let me just put a capacitor across here, pin 3 and 4, put a capacitor across here, and that'll need balancing up, I think. Put a cap across here and a cap across here. Relatively low values, I would have thought. I'm going to try 3 or 4 N, something like that, and give that a go. Okay, so I'm using 3.9 N in those 4 positions. I'm just going to plug that network in. I've just got this header here. Just zoom out here. Just got this header plug here, and I'm just going to plug it in on the caps that I've set up, so you can see the effect. It has quite a marked effect, as I would have expected. So that's as it is without them, and that's with that network plugged in. So some immediate changes. First of all, the bandwidth is obviously is a bandwidth the right term? The speed of the response through the power supply is obviously increased significantly. This here was measuring. Let's see. If I was to measure that just to this point here where it stabilizes, or where it appears to stabilize, that's about 130 microseconds. If I remove that network again, that's about 350 microseconds. That makes quite a big difference. Also on here, you can see the response time here dramatically improves. Yeah. Okay. Now the thing that hasn't resolved is this. We're still getting a 200 millivolt overshoot, which is a lot better than when we started, but it's still 200 millivolts. So I think, looking at this schematic, next thing I'm going to try and do is bypass this a little bit, because I suspect, there's capacitance here, there's a capacitive load here, and this is a resistance, quite a high value, 2K2, and I recall from early prototyping that this resistor value was quite sensitive. So anyway, I'm going to let me try and bypass it. I guess I'll start with 3.9 N again, because I've got some of them. Okay, so I'm just going to put that across 61 there. Okay, so that actually makes a difference. So an obvious question to ask there is, if I increase that value, will it improve that, or will it burst into oscillation? So let me try. So that was 3.9. I'll try 15N. So from 3.9 to 15, let's see what that does. Okay, so that definitely destabilizes it. So 3.9N. Okay, so what I think I'm going to do, I'm going to go and put these 5 caps in place on the actual board, so so I can I'll remove remove this, and then we can start looking at see if we can lower this. Okay, so I've fitted those caps into the circuit now, and that's the kind of response I've managed to get. It's certainly a lot better than it was. If you remember when we started this, it was overshooting by about half a volt, about 450, maybe 500 millivolts. So we're down to about 75 millivolts of an overshoot. I don't know how bad that is. I suspect now with the basic changes I've made to the circuit, any further improvement of that is going to start to get complex. So I thought what I'd do now is, before I carry on trying to do this, I'm going to benchmark the performance against some other power supplies that I've got. I just want to see what other power supplies do in this same configuration, and then once I've seen that, then I can make a decision as to whether I need to do any further work on that or not. A 75 millivolt, sorry, this is not 75 at all, it's 200 millivolts of division, so it's about 175 millivolt overshoot. You know, to me that does sound quite high, and I'd certainly like it to be better than that. But anyway, I'm gonna get a benchmark first, and then take it from there. As a comparative test, I've got a HP E3631A set up, also set to 5 volts, no current limit, running the same pulse test, so we can see the dynamic response of that power supply. This will give me some benchmark. At least I'll be able to know where I need to get to with my own power supply. So that's running now, and if we have a look at the scope over here, you can see that there's also an overshoot and undershoot, which is not a surprise. But let's have a look and see how that looks. So this is on the same scale as I was measuring previously, which is 200 millivolts a division, and you can see that it's significantly better here. In fact, that looks like about, let's have a look here, that's 100 millivolts a division. It's the overshoot we're interested in looking at, and that's at about, where are we? It's about 75 millivolts. Is the overshoot, and the same thing if we look at the undershoot, which is the inverse. The undershoot is about 100 millivolts. So that's a good reference point. I'm going to go on the assumption that if I can achieve those results or close to those results, then that'll be good enough for the power supply. Okay, so this is the test switching the power supply module on into a load, and you'll see here the switch on rise time. There's no current limit here, so this should be quite smooth. There it is. Very smooth transition from 0 to 5 volts into a load of about 1.25 amps. That's a 4 ohm load. So very, very smooth there. And this test is the power supply switching on into a load into current limit. So the power supply, the load is demanding 1.25 amps. I've got the current limit set to 1.1 amps. There you can see the again, nice and smooth, no overshoot. You've got this little oscillation around here. I'm pretty sure this relates to the diode. This is where the current amp kicks in and takes control of the current error amp. So I think that's just the switching around diode. It's certainly, I'm not worried about it at all. It's absolutely fine. So. Okay, so this is the dynamic response test. Exactly the same test we've done before, but now with the modifications made. And as you can see from the scope trace here, much improved over what I had before. If you remember the original but test was overshooting here by about 200 over 400 millivolts, which was quite significant. You can see now it's down to about 70 millivolts or 75 millivolts, which is very comparable to the test or the benchmark test that I've done with the Agilent power supply, so I'm pretty pleased with that. If you look at this trace, you'll see that there's a little bit of ringing, but it's very smooth. I'm really not worried about it at all. It certainly doesn't go unstable. I've tried a few variations of speed and so on. It's actually working really, really well. Conversely, there's also an undershoot, as we saw before. So if I trigger on that, you'll see it there. The ringing is a little bit more pronounced, but again, it is a ringing, and that's it stabilizes in 50 microseconds, so it's very, very fast. So I'm really pleased with that. I'm not going to try and improve on that for now. I think that's more than good enough, and I'll talk through the schematic now just in a moment to give you a sense of how that's been achieved. One of the things I thought I'd show you though was something I've discovered, because this pulse here actually is caused, believe it or not, by I'm just going to reposition the camera a second just so we can see both. These cables here are the cables that are running from the module to the DC load, and it's the inductance in these cables that actually has quite a big impact here. And if you watch this scope trace here, as I pull these cables apart, you'll see just by separating them, it increases the effect. And something I found quite fascinating was I took this ferrite, classic ferrite bead, and I wrapped it around the cables to see what would happen. It really had no effect. Then I took the same ferrite and I wrapped it around just one of the cables, and watch what happens. It actually sends it into an oscillation. Also, this makes quite a loud audible noise. I'm not sure if you'll be able to pick up. Let me just move the mic. So I thought that was quite interesting. Anyway, the long and short of it is these cables are it's quite important that these run together, and probably when they run inside a chassis, you would probably want to tie them together there. The tighter the coupling, you can see it improves it even further, and that's true on both the upper and the lower, the overshoot and the undershoot. So I thought that was quite interesting to see. I have one other thing you should be able to do is cancel this out with capacitance, and that's certainly also true. So if I just trigger on the other one here, and this is a 1000 microfarad capacitor, which is on the output of some power supplies, and if I put that across the output here, you'll see quite an immediate. In fact, it takes it down below the trigger level. There you go. So you can see the effect there, which is effectively cancelling out some of the effects of the inductance being placed on the cable there. Anyway, I'm actually really happy with that. I'm going to leave that. I'm not going to try and do anything more. I'll just what I'll do now is I'll take you through the schematic and show you the changes that have been made. So a roundup of the changes I've made to the power supply regulator to make these improvements. The first thing is the main goal was to speed up the servo path, just so there was a higher response. You would have seen that in the earlier video. And the starting point there was to look at this amplifier here, this differential amplifier. And all I've done here is put a capacitor between here and here, and here and here, and conversely on the other leg between here and here, and here and here. And what that serves to do really, as far as AC is concerned, it basically really lowers the AC impedance of this circuit. So if you imagine this leg here, for example, without that capacitor, you've got some capacitance here because of the input and the op amp, and you've got some inductance through these resistors, and the effect is you kind of get a delay through there at certain frequencies. So by bypassing that resistor, you don't impact the DC conditions at all, but any change on these inputs here is passed through much more quickly, basically bypass this resistor. Obviously picking the values, you know, I wasn't being particularly scientific, and I know you can work out what these should be based on the speed that you're trying to achieve. I use a little bit of trial and error and a little bit of common sense just to determine those values. What's important in this circuit though is whatever you do here, you've got to balance out on either leg, but you've also got to balance out on either side of the resistor divider that's setting the gain. So here and here, here and here. So that improved it up to this point here. Now the next thing was this resistor here. Again, same thing, you've got capacitance here, you've got a significant amount of capacitance here. This is actually in the circuit to stabilize that error amplifier. And again, you're looking for a high transition speed through here, and yet you've got this resistance, you'll have some inductance, some parasitic inductance there going into this capacitance, and the way to overcome that is to, again, add capacitance. Now, again, I used a little bit of trial and error, common sense. I used the same value just to keep the bill of materials down. That value worked perfectly fine. I doubled that value, I think I tripled that value actually. Put 15 in there and it burst into oscillation. Around about 10 it didn't, so I halved it again and you know, kept that there. So put that in to speed things up there. Then again, exactly the same thing on the output of this op amp, which is effectively the drive to the driver transistor here. Exactly the same thing again. We've got drive through this resistor, and I've bypassed that resistor this time with 100N. I mean, this isn't that critical. It just this is the DC conditions are important to keep this balanced. But speed isn't really a factor here. You want this to be as fast as possible. So 100N through there, also bypass this resistor with 100N, and also bypass this resistor with 100N just to speed things up around here. And so those are the modifications that allowed me to get much better performance, as you've seen. I've also done exactly the same thing down here on the error amp for the current limit. That's really improved things as well. That stopped it overshooting and picked up the performance. So they're the changes, and I'm pretty happy with that. The results aren't perfect, but they're certainly very, very good, and I think I'm happy to leave it there. You would have noticed I've changed this circuit around, and I've removed the multiple resistors from here. If you remember from the last video, heat was a real issue. 6 watts of, and bear in mind I've been working on the low voltage high current version, the 8 amp version of this module. So dissipating quite a lot of power in here, about 6 watts, and I've moved away from mounting them on the board because they just got too hot, and I've instead put in one of these, and that is a 0.05 ohm 10 watt resistor, Kelvin style resistor, so it's got the sense points on the centre 2 there. You can see I've changed the diagram to reflect that, so a relatively simple change. These things are actually quite expensive. I think they're about £5 each or £4 each or something. They're not cheap. Anyway, I've got a bunch of them for testing. I've got some 0.1s and some 0.05s. So yeah, so I've put those in there. So that's it. That's the changes to the schematic. Okay, so that's it. I've got to a point where I'm pretty happy with the regulator now. It's working perfectly, or it's certainly working as well as I expected it to work, and I don't really think I need to I don't think I need to do anything else with it. I think that's good enough. So I'm going to relay out the PCB now, get that ordered so I can build another couple of prototypes. I obviously need to implement the high voltage version. From the testing that I've done, I don't think it's going to be too much of a problem, but I still have to build it and verify it, so I'm going to do that. It's going to take me a while to get those PCBs laid out, that PCB laid out, sorry, and then the PCBs ordered. So I'll do that over the next 2 or 3 weeks. The next video post I'll do about the power supply will be relating to the firmware. I'll take you through the development environment. I'll show you the firmware, the code layout, and I'll get that available up on the blog, so you can download it and have a look at it and have a play around. Okay, so if you found the video interesting, you found it useful, please give it a thumbs up. Thanks very much for watching, and I'll catch you next time.